So today I wanted to talk to you about deviations from ideal behavior. That's basically anything that follows the ideal gas law. All of deviations from this perfect behavior are all sent around the kinetic molecular theory. So I wanted to kind of look into that one more time. So there were a couple different ideas included on the inside of kinetic molecular theory, such as gas particles have zero volume, that those gas particles are in constant and kind of random but straight-lined motion. The collisions of the container are elastic, which means that there's no net loss of energy, and they're also not gaining any energy. That the gas particles are neither attracted nor repelled to each other, and then also that the gas particles have this at the same temperature. They're all going to have the same kinetic energy. Now, we've talked about pretty much all of these at the same time. And we also said that anything that follows all five of these ideals is what we would consider to be an ideal gas. So again, an ideal gas is anything that would behave according to 100% of what we just wrote down about kinetic molecular theory 100% of the time. Unfortunately, inside of kinetic molecular theory, there are quite a few of these that we just don't agree with. Numbers 1, 3, and 4 to be specific. So any gas that violates these three rules in particular is going to demonstrate an ability to deviate from ideal behavior. That means that the ideal gas law has limits. It might work under some conditions, but not all conditions. And some gases behave more naughtily than others. So how can we tell which gases are going to behave more ideally and less ideally? Let's take a look at each one of these separately. So first of all, in rule number 1, it states that the gas particles have to have zero volume. But gas particles, real gas particles, actually do have volume. So what you're going to see then is that essentially the larger the gas particle is going to be, the less ideally it's going to behave. Specifically, the ideal gas law can predict the volume of a gas. But if the gas particles themselves also have volume, typically what we're going to end up seeing is that these real volumes of these real gases tend to be higher than what the ideal gas law can actually predict. And again, think about this. The ideal gas law assumes that the gas particles have zero volume. So if the real gas, their particles actually have some volume, it's going to add to that total. And again, that measured real volume will tend to be a little bit higher. This is a deviation from ideal behavior. Let's take another look at another one of these rules. How about that the gas particles have either no attraction nor repulsion? Well, that's absolute ridiculousness, because all particles have at least some level of attractive force. Everything at least has some van der Waals or London dispersion forces, and whether or not they have dipole-dipole or hydrogen bonding depends on their overall polarity, but everything has some attractive force. So essentially, the stronger that attractive force is going to be, the less ideal the behavior is going to become. Because if the particles are actually going to attract each other, they're breaking with this kinetic molecular theory. Now, this has an effect on the outward behavior as well. Typically, the stronger the intermolecular force, the more the gas particles are going to want to be attracted to each other. And if they're spending more time around each other, they're spending less time being randomly moving straight-lined motion gas particles. So typically we'll see that the volume of these gases is a bit lower than what the ideal gas law can predict. Now, this isn't the only thing that can actually affect whether or not our gas is behaving ideally. The gas laws typically only work perfectly if the material that you're working with is a gas. And I know that that sounds like, well, duh. But you have to remember that there are certain things in the environment that I can manipulate that would make a gas not a gas anymore. Let's take a look at this little simulation here of gas particles moving. Now, what I will be able to do is to manipulate the temperature. So I'm going to cool these gas particles down. Now, notice again, they're in random straight line motion. As the gas particles are cooling, they're also slowing down. Notice that at some point here, as they're slowing down, the gas particles are able to stick around each other a little bit more. Ordinarily, their super fast movement is enough to overcome intermolecular forces. But if they slow down too much, those intermolecular forces bring them together. This is no longer a gas. This is what I would call a liquid. And if we cool it even further than what we have seen here, we can get that molecular motion to slow down even more, and all of a sudden, a perfect crystal lattice appears. This is now a solid. The gas laws would not work on a sample that's in this state of matter. So let's take a look at all states of matter here. Just again, as a refresher, the gas laws are only going to work when you have a gas. So how can we turn a gas into not a gas anymore? Well, one thing that we can do is we can reduce the overall temperature. Now, as you just saw in that simulation, that's going to slow the particles down, and the intermolecular forces are going to start to take over. When the particles are moving fast enough, they don't have enough time to be near each other to attract. If I slow them down, those intermolecular forces make them attract, and we can condense our gas back down into a liquid or even as a solid. Another thing that we can do is to increase the pressure. One of the ideals of the kinetic molecular theory is that the gas spaces between these gases, the gas particles themselves, is immense. So if we increase that pressure, we're actually pushing the gas particles closer together. And anytime that those gas particles come closer together, those intermolecular forces can kick in. That means then that we can get those gases to condense back to either a liquid or a solid. And what about in the other direction? I can actually turn a gas into a whole different state of matter simply by increasing the temperature. I can turn a gas into a plasma by increasing that temperature. So again, I can increase that molecular motion to a point where that gas becomes not a gas anymore. Now, this is the least common example that you're going to see. In order to get a plasma, you're talking about crazy elevated temperatures like that you'd find on the inside of a star. So basically, the two major things that you can manipulate in the environment that will make a gas not a gas anymore is to reduce the temperature or increase the pressure. So again, most of your ideal behavior is going to function at either higher temperatures or lower pressures. Both of these states allow the gas particles to move quickly enough that they don't come near each other, and we're not pushing them together enough that the intermolecular forces take over. So again, just a couple random things here that either by the nature of the gas particles themselves or something that you can manipulate in the environment, you can actually get a gas to behave not like a gas anymore and become less ideal.